Pervasive and ubiquitous displays promise to extend beyond the physical boundaries of our devices, beyond our smartphones, smartwatches, laptop screens and monitors, and television screens. This leads to larger displays and more interactive surfaces. Despite the adoption of these technologies, there is low adoption of truly ubiquitous and pervasive displays due to the high cost and cumbersome deployment methods of these existing technologies. With traditional display technology, such as LCD screens, there are many layers, including row and column actuators, to trigger the red, green, and blue levels of each pixel through a color filter and ultimately creating an image. So, in this image on the right, with each pixel representing a different level of red, green, and blue, one can make out an image of an eye. The idea behind UbiChromics is the separation of the technology from the color elements. So we draw inspiration from the material science community, where we've looked at color-changing materials such as photochromic materials, and most people are already familiar with at least one example of photochromic material application, the use of transition lenses in glasses. Once the glasses are exposed to light, the chemical structure changes and the lens darkens. We call this process activation. Once the light source is removed, the chemical structure goes back to its original shape and the lens goes back to clear. We call this process deactivation. In our vision of UbiChromics, we make use of the color changing property with the light sources. So imagine a room where many surfaces are available to serve as displays. We could put a light source at the center of the room, and when the light source is turned on, a color change can happen on the surfaces, and this creates a display. The light source could then turn and create a color change on a different surface. A person could then interact with any of these displayed elements. In fact, could add to these elements as well, such as filling in the names of the states in the United States. So, the color changing areas is what we call the medium, and the light source that creates the color change is what we call the actuator. After evaluating 4 photochromic materials in 12 binders, we found that a ratio of 1:6 of photochromic powder to latex paint by mass worked best. To evaluate this paint, we created a light-proof box that we equipped with a UV light, a camera, and visible light. We placed a paint sample at the bottom of this light-proof box, turned on the UV light while the visible light was turned off, and recorded images over time. We turned the UV light off and then turned the visible light on while continuing to record, and we got a number of images representing the paint sample color over time. We then took these colored images and converted them to grayscale so that we can quantify the data. We took the mean grayscale value of each of the pixels in the images, as well as the standard deviation, to quantify the amount of contrast there was in the image. The lower the value, or the closer to 0, the darker the image was and the closer it was to black. The higher the value, closer to 255, the closer the image was to white and therefore less contrast. And so we plotted these values over time to determine the activation and deactivation time, or the amount of time required for the paint sample to go from clear to fully saturated, and then back from fully saturated back to clear. In this graph, we evaluated 3 samples, but I will point out the values of the paint that we used for our demonstrations. And in this case, it is garnet red. So to fully activate a paint sample from clear to fully saturated, it took about 23.3 seconds. And then with that fully saturated element, it took about 20.2 minutes to go from fully saturated back to clear. With the element of garnet red we selected for our demonstration purposes, we can paint it using traditional methods. And so here you can see that there's paint applied to the roller, and the roller is then used on the wall. The paint goes on clear and doesn't change color until activated by a light source. For the light source, we use a laser projector, and in this case, a modified commercial laser projector with a 405 nanometer laser diode. This allows us to have wide area coverage from a distance, and it allows us to connect to a computer via Ethernet cable to upload custom images and control with Python script. Not only can we upload custom images, but the Python script allows us to change which image is displayed, the size of that image, the XY coordinates, and the rotation of the image. In order to evaluate this, we did a user study where participants were asked to read various words that were activated for various amounts of time. We noticed that at 4 seconds, participants were able to begin clearly, confidently, and correctly identify words. And this 4 seconds of activation corresponds to a particular color. So at 23 seconds, once all participants were able to correctly and confidently read the words, there was a 100% color threshold. After 4 seconds, this color threshold was only 30%. And so we use this 30% as the minimum color for our system. This means that once a display has faded down to 30%, the light source would have to go back and project the display for it to get darker again. We also evaluated deactivation time as a matter of line length and activation time. So with the laser, we projected spirals of various sizes to equate different lengths, and we measured how long it took for them to deactivate back to clear. And so in this graph, you can see that as activation time increases, the amount of time for that displayed image to go back to clear also increases. And as we increase line length, the amount of time that the image remains on the wall decreases. So we created an equation for this model, and we compared line length to different characters. So in the example of a clock, which is 68 inches, we can estimate the activation time and the deactivation time needed to update the clock every minute. So with an activation time of about 6 seconds, we calculated a deactivation time of 53 seconds. So 53 plus 6 seconds is about 59 seconds, about a minute. So once the projection of the clock has faded, it would be time for another projection or an update to the next minute. So the system in its entirety is comprised of photochromic painted walls, the modified laser projector, a depth camera to pick up interactions, as well as a user interface. And there are certain elements that come with the system. A clock or dynamic elements that will update and refresh on their own, or custom text, which we call static elements or notifications, or a light switch and music controls, which we call interactive elements. And so in the user interface, a user can drag and drop one of the elements from the top here onto any surface of the painted area. The user can also switch which surface they would like to project onto. And then using computer vision and the depth camera, we can pick up interactions with those elements. And in this example, you can see the user actually selecting an element, dragging and dropping it to a location, that laser projector shining on to that known location, and then a user coming and interacting with the wall, and then a response happening. And in this case, the lights turn off. In this example, the laser projector has displayed a music menu where a user can press a play button, play music, or press a skip button to skip the song. And then the user has other functionalities, such as stopping the music and changing volume controls. So now that we've looked at UbiChromics with wide area coverage from a distance, we've also looked at it with closer up technologies. We created this smart pen equipped with a light source to activate the photochromic surfaces. Do you want to listen to some music? Yep. It also has a camera to detect the shapes that are drawn. In this case, a play button to play music. I think I'll skip this song. We also created a smartphone case that has an array of LEDs to display certain images, as well as time of flight sensors to pick up where the user's finger is and perform the corresponding action. In this case, a piano with the sound of the piano keys. All in all, UbiChromics and ubiquitous photochromic displays allow us to have scalability to existing surfaces, virtually anywhere. And these allow for larger displays in more interactive surfaces at a low cost of just a few pennies per meter squared. And the deployment is very easy since it uses traditional painting techniques. In the future, we could look at alternative mediums, such as longer lasting photochromic materials and different colors. I would like to thank my co-authors, as well as other members of the lab for their technical assistance, and the University of Michigan and NSF for their funding. Thank you. Are there any questions?